Wan 2.2 is currently one of the most powerful tools we have for making AI video, and in my last video we looked at how to use the standard nodes. But if you're finding that your computer is struggling to keep up or you're running out of memory, today's video is for you. Today we're switching over to the Kijai Wrapper. It sounds technical, but it's actually a much friendlier way for beginners to get better results. Instead of needing a massive, expensive graphics card, we're going to use 3 simple tools: memory swapping, SageAttention and Triton support. In this tutorial we're focusing strictly on the text-to-video workflow. I'll walk you through where to find the nodes, how to set them up, and how to get your first cinematic video running in minutes. Let's get started. First step, we need the Kijai Wrapper video wrapper. It's the secret sauce for speed. Go to your manager, click Install Custom Nodes and search for Kijai Wrapper. Hit Install if you already have it. Hit Update like I'm doing here to make sure you have the latest speed boosts. Wait for it to finish, then click Restart. Once it's back up, just refresh your browser. Easy. Next is for getting all the model.
Get your models ready. First, let's download the necessary models. You can access all the links in the video description below. For the Wan 2.2 text-to-video 14B model, we're using the GGUF quantized models because they are much smaller and VRAM efficient. Access the Hugging Face link. Unlike Wan 2.1, Wan 2.2 T2 V14B uses 2 models, high noise and low noise. We need both. So download both GGUF files. Choose the quantization based on your VRAM. I'm downloading Q5KS for both. These models run sequentially, not in parallel. You only need VRAM to accommodate the single largest model. Place both GGUF files in your ComfyUI/models/diffusion models folder. VAE model, for T2 V14B, you use the same VAE as Wan 2.1. Download it if you don't have it already. The download link is located at the same place with the Wan 2.2 models. Save the VAE model in ComfyUI/models/VAE. Light 2V LoRA. To dramatically increase speed, we need the Light 2V LoRA. The link is in the description. Save the LoRA model at ComfyUI/models/LoRAs. I'll be using rank 64 in this example. Text encoders. Finally, we'll use the Wan 2.1 text encoders. Download the UMT5 XXL PF16.SAF tensor and save it in ComfyUI/models/text encoders.
Now that we have everything installed, let's build the workflow. We'll start by adding the Wan Video Model Loader node. This is the brain of our setup that handles the actual video generation. Select the high model here. Next up is base precision. Precision is basically how much detail the computer uses for its math. I'm selecting FP16 fast. It's a special setting that speeds up your generations by about 20% without losing noticeable quality. If you're using GGUF models like I am, turn quantization to disabled. It's already built in, so we don't want to double up. For attention mode, we're using SageAttention. This is a huge memory saver. It keeps your computer from getting overwhelmed by the heavy video data. If you don't have it installed, just stick with SDPA for now. Now for the serious speed, we're using Triton. Connect the Wan Torch compile setting node to your loader. You don't need to touch the settings, just plug it in. A quick warning, using Triton requires Torch 2.7 or higher. Please make a backup of your ComfyUI folder before upgrading or installing Triton. It took me 6 hours to fix my environment when things went wrong, so definitely don't skip the backup. Finally, we're going to duplicate this entire node for our second stage. On this lower loader, select the low noise model. This model acts as the refiner that takes the rough shapes from the high noise model and adds the fine details, textures, and lighting. Make sure to connect the same Torch compile node to this one as well. Now let's talk about the most important node for anyone who doesn't have a $2,000 graphics card, the Wan Video Block Swap. If you've ever seen a CUDA Out of Memory error, this node is your best friend. In simple terms, block swapping allows ComfyUI to move pieces of the AI model off your graphics card and into your regular computer RAM when they aren't being used. The blocks to swap setting tells the system how many parts of the model to move. The Wan 14B model has 40 blocks total. Every block you swap saves about 300 to 400 MB of VRAM, so if you swap 20 blocks, you're freeing up nearly 7 to 8 GB of space on your GPU. You'll also see VACE to block swap. VACE is a separate model used for specific video editing tasks. Since we aren't using it for this basic text-to-video setup, we're leaving this at 0. There's also prefetch blocks. This is a speed setting that tells the computer to start loading the next block while the current one is still working. Setting this to 1 usually keeps things moving smoothly without causing error. To actually apply these savings, we need the WAN Video Set Block Swap node. This is like the adapter that plugs our settings into our models. First, connect the high noise model loader to the model input, and then plug our block swap settings into the block swap args input. Now just duplicate that node. Connect this one to the low noise model loader and share the same block swap settings. By doing this, both stages of our video generation will use less memory, making the whole process much more stable for longer videos. Now we're going to add a secret ingredient for both speed and quality, the WAN Video LoRA Select node. In the list we're selecting the Light 2VT2V14B CFG Distill V2. This is a distilled low RA. Think of it like a shortcut. It teaches the model how to get high-quality results in fewer steps, which saves us a ton of time without losing detail. Now here is a pro tip for the settings. For the high noise strength, we're going all the way up to 3. Since the high noise stage handles the bones of the video, the motion and the physics, we want this low RA to work extra hard here to make the movement as fluid and realistic as possible. Next, just duplicate that node for our second stage. But for the low noise model, we're lowering the strength to 1. In the low noise stage, the video is already mostly built. To apply these, add the WAN Video Set LoRA node. Take the output from our Set Block Swap node and plug it into the model input here. Then connect our low RA settings to the LoRA input. Finally, duplicate the Set LoRA node one more time. Connect your low noise model chain to this one, and plug in the second low RA node we just made. Now both stages of our generation are perfectly tuned for speed and professional-looking motion. Now let's bring it all together with the WAN Video Sampler. This is where the magic happens. We're going to set this up for maximum speed and prompt control. First, for the steps I'm using 8. Since we are using the distilled low RA, we don't need 20 or 30 steps. 8 is the sweet spot for fast, high-quality results. For the CFG, we're using the CFG schedule float list. Connect your steps integer to this node too. Now remember the Kickstart hack set both the start and end to 2.0 but set the end % to 0.01. This makes sure that the AI only uses that strong CFG of 2 for the very first step. This forces the AI to follow your prompt immediately. Next, set the shift to 8. In Wan 2.2, shift controls the noise schedule. A higher shift like 8 keeps the model focused on the big picture for longer, which leads to much better composition and more stable motion. For the scheduler, I'm choosing DPM++S. For the image embed, we'll use the WAN Video Empty Embed. We're sticking with the default size and setting it to 81 frames, which gives us about 3 seconds of smooth video. For the text, I'm using the cached text encoder. This is another speed boost. We're selecting the UMT5XXL model and setting the quantization to BF16. This gives us the smartest prompt understanding without eating up all your VRAM. Finally, look at the end step. I'm adding one more integer here and setting it to 4 or half of total step. Why 4? Because Wan 2.2 is a mixture of expert system, we only want the high noise model to handle the first half of the work. After that, we'll hand the video off to the low noise model to finish the fine details. Now that our first model has sketched out the video, it's time to hand it off to the second expert. Duplicate your WAN video sampler and let's set up the low noise stage. Connect your step integer, the 8 we set earlier, to this node too. But here is the trick. Take that end step integer set to 4 and plug it into the start step of this new sampler. Now for the CFG, we aren't using a schedule this time. Set it to a flat 1.0. For the model, make sure you connect your low noise set LoRA chain here. For the image and text embeds, we can just share the same ones we used for the high noise sampler to keep the workflow clean. Finally, the most important connection, take the samples output from our high noise sampler and plug it into the samples input here. Right now our video is still just latent data. Basically it's just a bunch of math that we can't see yet. To turn it into an actual video, we need the WAN Video Decode node. This node needs a VAE to work. Think of the VAE as the translator that converts the AI's internal language back into pixels. I'm using the Wan 2.1 VAE here. Connect the samples from our low noise sampler into the decode node. Now to actually save and view our file, add the Video Combine node from the Video Helper suite. This is where you can choose your format like MP4 or GIF. For the frame rate, I'm setting it to 24 FPS. And that's it, our blazing fast, high-quality Wan 2.2 workflow is complete. Let's hit Q prompt and see what we've created. So here are the results. Pretty incredible, right? The quality is sharp and the motion is fluid, but the real headline here is the speed. For this first generation, including the time it took to load the models into memory for the very first time, it only took 336 seconds. To put that in perspective, when I ran this same setup using only the standard ComfyUI core components, it took about 13 to 14 minutes on the exact same hardware. I'm running an RTX 4060 Ti with 16 GB of VRAM and 64 GB of RAM, and we've essentially cut the wait time in half. The second video was even faster because the models were already warmed up in the memory. It took just 299.56 seconds. Previously, even after the first generation, the core nodes were still taking 8 to 10 minutes per video. We are now consistently around 5 minutes. Our third sample came in at 308.86 seconds. As you can see, the consistency is there, but I wanted to see if I could push it even further. I decided to test the prefetch block setting. In theory, setting this to 1 should offset the time lost during the block swap by loading the next piece of data while the current one is still processing. I ran the test, and while it was technically faster at 295 seconds, it wasn't a massive leap. To be sure, I ran it again, and that time it took 306 seconds. So my takeaway for you, while prefetching is a cool feature, it doesn't seem to be a magic bullet for speed on this specific setup. The real heavy lifting is being done by the Kijai Wrapper and those Triton optimizations we set. Now let's talk about the specific settings for your hardware. If you're on a card like mine, the 16 GB 4060 Ti using 20 blocks works great, but it does sit right around 14 GB of VRAM during the generation. If you have a 12 GB card like an RTX 3060, 20 blocks using the Q5KS model will likely give you an out-of-memory error. You have two choices. Either switch to a lower quantization like Q4KS or Q3, or you can simply increase the number of blocks we're swapping. I did some testing for you. At 25 blocks, the VRAM only drops to about 13.1 GB, which is still too high for a 12 GB card. The time stays consistent at about 310 seconds. At 30 blocks, we finally hit the sweet spot for 12 GB users. It uses roughly 11.8 to 12 GB of RAM. It's tight, you'll definitely want to close your browser tabs and other apps, but it works. Even with my OBS recording and a bunch of Edge tabs open, it still finished in about 310 seconds. But if you want to be completely safe on 12 GB, go with 35 blocks. This drops your VRAM usage down to a comfortable 10.6 to 10.8 GB. However, there is a trade-off. Blocks that aren't on your GPU go to your system RAM. If you have 35 blocks swapped, you'll need about 10.5 to 14 GB of available system RAM. If you have 16 GB of total RAM or less, this might cause a crash, but if you have at least 32 GB of RAM, this is the safest, most stable way to run the high-quality models. The best part, even at 35 blocks with prefetch set to 1, the speed stays right around 310 seconds, so don't be afraid to increase those blocks to save your GPU, it won't slow you down. And that wraps up our deep dive into the high-speed Wan 2.2 workflow. I want to give a huge thank you to everyone for following along. We've managed to turn a 8 to 10 minute render into a 5-minute masterpiece, all while keeping our VRAM in check. I've made things easy for you. The full workflow link is available in the video description below. But that's not all. I've also included a bonus upscaler and a dedicated interpolation node in the file that will boost your final result to a buttery smooth 60 FPS. It's the perfect way to give your AI videos that professional high-end finish. If you found these speed tests and hardware tips helpful, please hit that like button and subscribe to Cao 2025. It really helps the channel grow and lets me keep creating these deep dive tutorials for you. Got a question about your specific GPU or a prompt that isn't working? Drop a comment below. I try to answer as many as I can. Don't forget to share this with your fellow AI creators who are tired of waiting 15 minutes for a single video. Thanks for watching, and I'll see you in the next one. Please subscribe.